Hello, Kennedy. Hello, August. Nice seeing you connected. Whew. So, thanks to those who submitted the last homework. I hope you enjoyed it, and it will be a good fundamental for our next steps forward. For the sake of time, probably we will either skip or postpone self-grading. I don't know if you liked this activity or it was additional exercise. But I'll either skip completely or do it next time. I will show the key and give brief comments so that we are on the same page. And then we will continue the motion towards dynamics for harmonic oscillators, right? Which corresponds to several examples. Before we go forward, let's try to recall. Please try to give examples of harmonic oscillators, which physical, chemical systems can be described by the model of harmonic oscillator. And August and Kennedy online can also unmute microphone and say or type.
Hydrogen bond, moving back and forth.
Okay, so molecular hydrogen. Okay, one.
Movement of electrons around the nucleus.
No, it's not harmonic. It's Coulombic force, which is 1/r instead of r squared. And when they close to each other, there is a repulsion, but they explore the whole range, and harmonic oscillator is not a good approximation.
Weight on a spring.
Okay, yeah, good.
Solvent.
Excellent. So vibrations of solvents. What about so you should know chemical nomenclature. If you have 2 carbons and 3 hydrogen to each, C2H6. What's the name?
Thing.
Okay. What if they rotate? One methyl group rotates around another one.
Overlapping.
So there will be different way of steric interaction. And since it is periodic motion, there are preferred angles. And there are equilibrium near preferred angles, which will also behave harmonically. What about cell phones, radio transmitters, radio receivers?
Capacitors.
Capacitor inductor circuit. Right? So we have about 4. What about gold, nanoparticles, metal? If it is small between molecule and solid, why does it absorb and emit light?
Because of the photons exciting it.
Yes and no. If we have molecules, photons excite them. But if you have metal nanoparticle, there is a collective motion of all electrons, which is quite harmonic, and it determines frequency of absorption and emission. So it is the phenomenon of plasmons, because same process happens in the ionized matter when all electrons and all ions move in comparison to each other, right? What else? If you have 2 mirrors and you catch electromagnetic radiation between mirrors so that it cannot escape, is there anything harmonic there? based on the question, it should be,
Yes.
right? So what is oscillates harmonically in the resonate? So we don't have time right now, but I want either to believe now or to make my effort by the end of the course that we all know how lasers are principles of lasers. Right? So it's two mirrors and some active medium. And the amplitude of electric field for this electromagnetic radiation behaves according to the same harmonic oscillator law. So 6 should be enough. Okay, so what is the goal? The number of slides is not as big, so we can do in a little slower mode. So we are in the physical chemistry course. Our original goal was to describe properties of molecules based on the fact that electrons are waves. And later on, we discovered that nuclei and several other examples may exhibit quantum properties. And now we are applying all skills from quantum theory to harmonic oscillator. So we did set up Schrödinger time-independent Schrödinger equation, and we made a bypass of finding eigenstates through the concept of Stroman annihilation operator. Acting on the lowest state gets 0. This gives the ground state. Then by applying creation operators, one creates excited states. What else? Creation and annihilation operators are linear composition of position and momentum, and based on your homework, position and momentum are linear combinations of creation and annihilation. Right? Where are we going? We do want to complete our transition to discrete basis of eigenstates, and there we are going to see what happens if the harmonic oscillator, which as chemists our primarily understanding it is interatomic bond, is being excited by infrared laser, or by some reason amplitude of oscillations increases. And in order to describe this process, we need to find an eigenstate of annihilation operator as an auxiliary tool. Do I agree with myself before weekend? Okay. So did you found the link in the email?
Yes.
Can you edit it?
Yep.
Okay. So today there is no time to go over this stuff once again, but please consider to make your choices, and you can either connect subject and your name by an arrow, or type your name near the.
So do we pick just like C, or do we
pick more specific, and you can type something. Describe your problem.
How specific? Like C1 or C Roman numeral 1?
The more specific, the better. Ideally, I would be very happy to take kind of personal interview with everyone and learn what is your project.
So like that?
Huh? Excellent, excellent. Yes.
Is that good?
It is good. It is good. It is good. Yes. And Kennedy and August are also welcome to make these connections. We will start doing projects coming Wednesday evening. So you still have a couple of days to redecide, but I want to adjust my thoughts and plans how to help. And if you make choices, okay, yeah, thank you, Kennedy. And if your favorite project is not typed, do not panic. You can either type it or just tell that I have a special choice. Let's discuss it later. Okay, thank you. show and announce some keys so that you feel more comfortable. So the creation and initiation operators are different from each other by the fact which of the subdiagonals they occupy. So for the initiation, it is upper subdiagonal. For creation, it is lower subdiagonal, and it has a progression of a square root of number factor in front of it. First diagonal, subdiagonal, lower and upper. So basically, we instantaneously get the second one. So if one writes down the definition of creation and initiation operator, like 2 lines, and solve them for position and momentum, then one can find that their summation is position, their subtraction is momentum, and the factors include imaginary unit for momentum, and both of them include constant and mass and frequency, but it swaps between the nominator and denominator. So if each of the operators is lower and upper subdiagonal, by adding together it will be both upper and lower subdiagonal. So basically square roots of 1, 2, 3, 4 along the matrix, and appropriate factors on the side. If one wants to find whatever is needed, like kinetic and potential energy, one just takes this definition of position and momentum and plugs it into the definition of potential energy, so mass frequency squared, which is rigidity constant divided by 2, and then x squared. And if one carefully plugs this stuff here, then a lot of factors cancel, and then one would have the 4 terms, this creation and initiation in different order. Creation squared, initiation squared, and then a dagger, A. If one plugs in the momentum into definition of the kinetic energy, momentum squared over 2 masses, also stuff is canceling, and one also has 4 terms, but the interesting observation is that the sign inside the bracket are different between the squares and first terms. And if one adds together kinetic and potential energy, the square terms cancel each other. And if one performs it, the factor up front adds together, so h bar omega over 4 twice will be h bar omega over 2. And then one is getting a dagger plus a dagger A. So right now we are not doing collective editing, but going up to this line is a full credit, and stuff here is just more standard way that is related to the next term.
And if we wrote it in the more standard way, is that still full credit?
Oh yes, absolutely. Well, if I develop some doubts that you derived it rather than remembering, I may destroy a little. Any questions from August, Kennedy, Jared, and Zay? No? Okay. So, do I need to give any comments about this top line? Is it like self-evident, or you want me to? Are you sure?
Well, I'll get there.
Sure, I'm good. August and Kennedy. If you have doubts, or if you want me to give some comments about this stuff in the blue circle, and happy. Okay, so just in case, if one plugs in definitions and then recalls the commutation of, so this rectangular brackets correspond to commutation, one direct order minus inverted order. If one plugs in definition of AA daggers for position and momentum, then and uses commutation of position and momentum, which is like proportional to h bar, then one will derive this stuff. And commutation of position and momentum is non-zero because of the differential operators. We covered it at the quite beginning of the course. Now, the next step. Before, of course, you can read it without me, but I saw you progressed quite well in doing. But why this problem was asked? Is there any necessity, rather than torturing young brain and giving exhausting you and exhausting me? So I assure you, this is not a purely abstract exercise just to count mathematical masses. There is a very big positive outcome that we will cover on lectures. So let's keep the chat. Ways to describe experiments to predict future. So we have evolution operator, Schrödinger equation, right? And if we are focusing on the observable that we want to compare with the experiment, what is the alternative to Schrödinger equation? When we need to find expectation value, and instead of sandwiching operator between wave function, we want to compute trajectory of certain observable, expectation value of an observable right away without wave function. The last name starts with letter H.
Heisenberg.
Yes. So Heisenberg and his equation of motion helps to find observable in its trajectory without knowing wave function. This approach will be very, very soon needed and helpfully useful to answer our set of questions. What would happen to interatomic bond when it is irradiated by infrared laser and it is pumped up? So it would be really cool to look on how the average position of the wave packet, how the expectation value of interatomic distance goes with time. The standard ways to wave function is possible, but it is painful. The Heisenberg equation of motion applied directly to position and momentum is easier, but also not the easiest one. And later on, and I will start declaring it from scratch, I'm just giving a little heads up. If one writes down Heisenberg equation of motion for operation and annihilation operators, one would simplify all calculations like at least by order of magnitude. So later on, we are going to practice Heisenberg equation of motion for the operation and annihilation operator. And we will be in a rush, and I do not want to waste time on the next meeting. So we are finding commutation between Hamiltonian and annihilation operator. So A dagger A 1/2, comma A, which means I do not have speech defect. I'm just trying to read what is written here. Minus and one puts cross whenever it's needed. So you see that this dagger is first time it is here, and second time it is here. So the this A comes first at the end, and second time comes at the front, right? And then one can look on the stuff, focus on different set of factors. And if one looks on the first two factors and applies this property, then one can replace it lowering annihilation and creation, and replaced by creation and annihilation plus one. So we plug it in, and then we are getting the same order. So A dagger A, and then multiplied by A once again, right? So A dagger A, and in the first term we also have A dagger A. So they cancel. And then this plus one multiplied by A gives one more term. So after this commutation, we get minus A bar omega A. So by exploring commutation of annihilation operator with Hamiltonian, we get back annihilation operator. It's a good luck. It's not. It doesn't happen all the time for any Hamiltonian any operator. So it is quite appetizing from mathematical point of view, and therefore harmonic oscillator is a favorite toy of large number of scientists. So if one explores commutation with A dagger, one practices the same stuff, like opening the bracket and then focusing on the set of factors that is convenient for us. And where is the logic? The logic is that I intentionally want to have the same set of terms that can be cancelled. So I'm just trying to look which part can give the same thing. And by commuting Hamiltonian with creation operator, one gets creation operator back. So we are going to use this property rather soon, and I will just refer to this homework. Any questions about this stuff? I got some emails requesting additional comments. Did I address all of them, or there are more questions? 1/2 is removed because constant commutes with anything. Okay. If there are questions from August or candidate, please let me know. And okay, let's see questions. So going forward. So here was the list of expected outcomes that we decided to pursue last time, and we are going a little bit slower than originally planned. So by the end of today's meeting, I would like to get this relation, this equation. And the goal is, once again, to describe dynamical processes that happen with any object that is modeled by harmonic oscillator. Our primary interest and focus is an interatomic bond that is excited by infrared laser. In order to pursue, we are exploring eigenstates of annihilation operator, which is like annihilation operator acts on unknown wave function expanded in the phase set, gives the same wave function with unknown eigenvalue. So if everything goes favorably today, we will find that the expansion coefficients in this unknown eigenstate will be obeying the recursion relation. So they are not independent from each other. So the expansion coefficient of the senior order is depending on the expansion coefficient of the junior order. And upon proving this stuff, we will see that eigenvalue and eigenvectors are connected to each other. And after this point, it will be quite easy to find the overall answer. But we are trying to do practice the principles of attention almost divide and conquer. So if you do everything at once, it will be probably too much for one meeting. So if we arrive to this box, it will be sufficient for today. So the annihilation operator converts the eigenstate of the higher number to eigenstate of the lower number. Okay? So it was in the homework that you just submitted and what we discussed in the key to the homework. So matrix with upper subdiagonal with square roots. I'm going to plug in this definition here and then practice which property? Let's briefly discuss the definition. You are trying to solve this equation for high. And suppose we are not in a rush. What would be the strategy? So, what is unknown? Eigenvalue. Eigenvalue. Let's suppose that it is known. What else is unknown?
CN.
Yes, expansion coefficient. Do we know angular bracket of n eigenstates?
Yes.
Do we need to find them? No, we already know.
No, we already have them. Yeah.
So, do we need to carry them into our equation? Would they be included into the answer for the C sub n?
Yeah.
No. So, we want to get numbers, and eigenstates are abstract stuff. So, we want to get rid of wave functions, of eigenstates. Right? And which practical step helps to get rid of the eigenstates? What do we expect from any good functions that someone sells to us? Like if I'm shopping in the supermarket for good eigenfunctions, what is my criterion? What are my expectations?
The function.
Yeah, what is to be a good function?
Wave function operator.
Yes, and how do they relate to each other? What would happen if I take
observable, right?
All good, all correct. But what if I take function with itself, like absolute value square of the function, integrate? What do I get?
The next higher term.
if I take good wave function, take absolute square, and then integrate over the whole range of definition.
Positive.
Positive. What else? Anything more specific?
Is it Gaussian?
No. Wave function is distributed, but after integration it will be a number.
Real.
Real, positive. But if the eigenstates were found in a correct way, there is
Whole number.
Everything is correct. And now I see. I cannot stop myself from telling a joke. Cloudy day. Person with a dog is walking on the square. There is strong wind, rain, and suddenly a balloon with a traveler sets in the center of the square. The traveler is very stressed because it's a hard condition for traveling through the air, and he calls to this stranger with a dog and, help, please tell me, where am I? The person with the dog stopped, thought for a minute, and then answered, you are on a balloon. And then the wind took the balloon out. So evidently the person on the square was a mathematician, because he was thinking before answering. He was giving absolutely correct answer. And third, because this answer didn't help anyone. So let's try once again. What is the property of a good wave function? One of the properties that really helps to get rid of wave functions, to find eigenvalues. And I'm not expressing it in the best possible way because I'm confident you all know it.
It oscillates?
No, time independent Schrödinger equation.
Does it equal 1?
Yes, exactly. So it's normalized. Everything you told was correct. It's positive. It's real. It is one of the integer numbers. Okay, what if we take two basis functions, two eigen functions from a set, multiply them and integrate?
For 1? For 2?
0. So, and together, if same as if you have vectors in two-dimensional space, if they are collinear, if it is the same vector, the scalar product will be 1. If they are 90 degrees, scalar product will be 0. So orthogonal. And when one normalized, and people combine it into one word, orthonormal, right? So orthogonal and normalized. So this is a property that is widely used in all derivations. When we need to get rid of a wave function, we assume that n times n equals 1, n times n equals 0. Right? It is the same as if one would it is the same as if one would write I m x equals delta m, right? So we are going to plug in this red box into main equation and seek if this bra and this cat here and this bra and this cat will match orthogonality. through practicing orthonormality relation, we will get rid of brass and cats wherever possible, and then try to find connection, some equation for C sub n. Make sense? So top line unknown so eigenstate, operator, eigenvalue. Now we can take this bra and put it inside a bracket and just have two summations, right? Because we do not swap anything. If you do not swap order, then we can reshuffle stuff. And by the orthonormality relation, this k plus 1 and n will be 0 if these two numbers are not equal, or 1 if they equal. And we symbolize it by delta k plus 1 comma n. So it means that in all these extensive summations, most of the terms will be zeros. And for only very specific values of n and k, it will be non-zero. So it's like a snake eating a mouse or a rabbit. Summation and delta function cancel each other, and as a price, one needs to plug in the specific value. So wherever we have n, we need to plug in k plus 1. Make sense? Mm-hmm. And I do not like stuff here. It should have the A also written on paper. Oh no, it's fine. We were not applying A. So what's the reason? All good. Yes. I just have fear to make errors. So if n equals k plus 1, then k equals n minus 1. Then everywhere where we have n, we can put n minus 1. So or we have k, we put n minus 1. So k replaced by n minus 1, k replaced by n minus 1, k replaced, and here this disappears. And here we have c sub n stays. Now we have one summation less, all the way over n. And here is an interesting observation. On the left and right, we do have summation over the same index. On the left and right, we do have the same basis set. On the left and right, we have like two series expressed in the same basis. And the idea is that one plus c 0 1 c 1 c So two series, and there are more terms. Two series will be equal if because the basis sets are the same, they will be equal only if the expansion coefficients are equal. Make sense? So to have for easier counting, I'm just replacing n minus 1 to n, and then n to n plus 1 to have absolutely the same counting. And then in this expression, I do see that coefficients by the same basis sets must be equal by the rule of processing series. But here they are different. So here C sub n is multiplied by the eigenvalue, and here is multiplied by this square root of n plus 1. So if we divide both by square root of n plus 1, we will have our recursion relation, which means as soon as we know the lowest expansion coefficient, we can find the first one. As soon as we know the first one, we can find the second one. And then we run up, and through this recursion relation, we find all of them. So basically, now we need to find only two things, mu and C naught. I believe it is the last thing for today. Meeting is done. Everyone is welcome to disconnect and depart. If